Okay, so let's take a look at our first continuity examples here. We got part A and part B. If you haven't had a chance to work these yet, I suggest you just go ahead and pause the video and work these beforehand and then come back and see how you did. Okay, so I'm going to start with our first test of continuity, and that's to determine if the value is defined if the function is defined at the value. And so here we have a cubic function, and we want to see if it's defined at x equals to 2. And so what we'd basically do here is we would just simply evaluate this function at 2. And we can see that that is going to equal to 11. And so we know we have a point on the graph that is 2, 11. And so we know that it's continuous at that point, or it's defined at that point, excuse me. Now, the second part of this is to determine if it approaches the same value from both sides. And so what we need to do is we need to create a couple tables using values that get closer and closer to x equals to 2 and see if it approaches the same number from both sides. Now, this will have a lot of decimals. I already have the tables completely done, so I'm not going to go through the calculations, but what I'll do is I'll go ahead and fill in the tables, and you can just double check your numbers to make sure that you have the right information. Okay, and what we should see here is that once these tables are completed, that both output values, the output values from both sets of tables, you can see as we get from 1.9 to 1.99, we get closer and closer to 2, that this number seems to approach 11 from this side. And so same thing from the other part. As we get from 2.1, 2.01 and get closer and closer to 2, this seems to approach 11 from this side as well. And so 11 is really not necessary in the second part of the continuous test. The fact that it's approaching a similar number from each side is what's important. And of course, the third test is to determine if it is approaching the same value. And so it seems to be approaching y equals 11 from both sides. And so that tells us that this function is continuous at x equals to 2. And so we've passed all three parts of the continuity test. Okay, let's take a look at part B. Let's see what part B is going to present us with. Now we have a rational function here, and from a graphing standpoint at this point in time, it probably would not expect you to understand what's going to happen with this particular function. You could punch it into your calculator and you could see what it would give you. But we are really just trying to see if this thing is continuous or if it's gonna break apart somewhere, or what exactly it's gonna do. And so we need to go through our basic test. And so our very first test is just to see if it has an output value for x equals -3. And so we'll just go ahead, we'll go ahead and evaluate this at -3. And so I'm going to go and plug in -3 for all x values in the entire function. And I just like to keep using parentheses to stay consistent all the way through the function, even if it doesn't have a higher degree exponent. And so as I do this, you can see, regardless of what happens on top, we end up getting a 0 on bottom. Which means that this is going to be undefined at f is -3. So we can say that f of -3 is actually undefined. Now, we haven't passed the first test of continuity here because it's not defined at x equals -3. So it can't be continuous at -3. And so we basically know that at this point, at x -3, it's discontinuous. And so we can make this statement: since it's discontinuous, at x equals -3 that it has point discontinuity. And you would not even have to continue with the second and third test. And so that would be the end of this particular sample problem. So hopefully you were able to mathematically prove the continuity or disprove it with the given continuity test.